Some problems take a few hours to solve. Others take centuries. These aren't puzzles for extra credit. These are the Everest of mathematics. They baffled the smartest minds on Earth, shattered assumptions, and in some cases, changed math forever. Today, we're counting down the top 10 most complex math problems ever solved. Problems that weren't just difficult, they redefined what humans thought was provable at all. We rank them based on 5 key factors: the complexity of the problem, the difficulty of the solution, the impact on modern mathematics, historical importance, and how groundbreaking the solving method was, from problems that took supercomputers to verify to equations that resisted solution for centuries. We'll explore the brilliant minds who finally cracked them. And trust me, stick around for the top 3. One took 10,000 pages to prove, another sparked a mathematical revolution, and one was solved. Then the genius who solved it vanished. This isn't just a countdown. It's a journey through the most legendary problems in the history of math. Let's begin. Imagine a math problem that proves math itself has limits. In 1931, a quiet Austrian mathematician named Kurt Gödel shook the foundation of mathematics with a pair of theorems so profound they still echo through logic, philosophy, and computer science today. Gödel's first incompleteness theorem says that in any consistent mathematical system, there will always be true statements that can't be proven within the system. Yes, math is incomplete by design. His second theorem was even bolder. No consistent system can prove its own consistency. In other words, we can never be fully sure that math isn't hiding contradictions somewhere deep inside. This was a direct blow to David Hilbert's dream of a complete, flawless system of logic, a dream shattered with absolute precision by Gödel's genius. Gödel's work didn't just change math, it laid the groundwork for modern computing, proof theory, and artificial intelligence. Uncertainty is not just possible, it's inevitable. If Gödel showed us the limits of logic, the next problem asks, can we automate solving equations? Let's go to number 9. Can there be a machine, a procedure, that decides whether any given equation has a solution? That was Hilbert's 10th problem, posed in the year 1900. He asked, is there an algorithm to determine whether a Diophantine equation, one involving only integers, has a solution? Seemed straightforward, but it wasn't. For decades, brilliant minds chipped away at it. Then, in 1970, a 22-year-old Soviet mathematician named Yuri Matyasevich cracked it, proving that no such algorithm exists. That means there's no universal method, not even with infinite time, for solving every Diophantine equation. It was a huge blow to the dream of full automation in mathematics. Matyasevich's proof, building on years of groundwork by others, became one of the most elegant endings to Hilbert's problems and a milestone in computability theory. From abstract logic to colorful maps, our next mystery was so deceptively simple, it fooled the world for over a century. It sounds simple. How many colors do you need to shade a map so that no neighboring regions share the same color? This innocent-sounding puzzle stumped mathematicians for over a century. First proposed in 1852, the 4-color problem became one of math's longest unsolved mysteries. No one could prove if 4 colors were always enough for every map, no matter how weird or wiggly the borders got. In 1976, Kenneth Appel and Wolfgang Haken used a groundbreaking method, a computer-assisted proof. They divided all possible maps into 1,936 different cases and had a computer check each one. It worked, but it sparked a huge debate. Could a proof be trusted if no human had verified it by hand? Was this the future, or cheating? Despite the controversy, it changed mathematics forever, ushering in the era of computational proof, where human insight and machine logic work side by side. A coloring puzzle that redrew the boundaries of mathematical tradition. We're done with maps. Now it's time for oranges. No, really. Number 7 began in a fruit market and ended in a supercomputer. In 1611, Johannes Kepler, yes, the planetary motion guy, posed a question about oranges. He asked, is the way grocers stack oranges, called face-centered cubic packing, the most efficient way to fill space with spheres? It seems obvious, but proving it? Not so easy. This deceptively simple question became known as the Kepler conjecture, and it took nearly 400 years to solve. In 1998, Thomas Hales submitted a computer-assisted proof, so complex, reviewers couldn't verify it with certainty. It wasn't until 2014, using a formal verification system called HOL Lite, that the proof was finally confirmed line by line, by a computer. The result? The face-centered cubic pattern, yes, the way we stack oranges, is mathematically perfect. A 400-year-old mystery solved with algorithms, geometry, and a little help from the produce aisle. Imagine trying to catalog every possible atom of symmetry in the universe. That's what mathematicians set out to do. With a project so massive, it took over 50 years to complete. It's called the classification of finite simple groups, a monumental effort to list all the building blocks of symmetry, like a periodic table of pure logic. Finite simple groups are the prime numbers of symmetry, basic units from which all other groups are built. And there are exactly 18 families, plus 26 rare exceptions, known as the sporadic groups. One of them, the monster group, has more symmetries than there are atoms in the Earth. The full proof spanned over 10,000 pages, involved hundreds of mathematicians, and stretched across 4 decades. Some called it the mathematical moon landing. In 2004, the final pieces clicked into place. It wasn't one person's triumph, it was a symphony of collaboration, logic, and persistence. From a project that spanned decades to a revelation made by two young geniuses, one of whom died in a duel before his theory changed math forever. You've probably learned how to solve a quadratic equation, maybe even a cubic. But what about a fifth-degree equation called a quintic? For centuries, mathematicians searched for a formula, just like the quadratic one, that could solve every quintic. They failed. And then came Niels Abel. At just 22, Abel proved it was impossible. No general algebraic solution exists for the quintic. He didn't just fail to solve the problem, he proved the problem couldn't be solved. Then came Évariste Galois, a teenager who reimagined the entire concept of solving equations, not with numbers, but with symmetry. He invented group theory, one of the most powerful tools in modern mathematics, all before the age of 21. The night before he was killed in a duel, Galois scribbled his entire theory in a frantic letter. That letter laid the foundation for modern algebra. The solution to the quintic wasn't a formula. It was a revolution. Solving equations is great, but what if we asked, does every equation have a solution at all? That's what a 22-year-old Gauss set out to prove. Every equation has a solution. That simple idea powers everything from rocket science to machine learning. And it all begins here, with the fundamental theorem of algebra. It states that every polynomial equation, no matter how strange, has at least one solution in the complex numbers. Seems obvious now, but in the 1700s, it wasn't. In 1799, Carl Friedrich Gauss, at just 22 years old, submitted his doctoral thesis. In it, he proved the theorem using a blend of geometry, logic, and brilliant insight. This wasn't just a solution, it was a turning point. It linked algebra with geometry and gave rise to entire fields like complex analysis and algebraic geometry. Gauss would go on to become one of the greatest mathematicians in history, but this, his first major work, was the proof that launched it all. Now let's talk primes, the atoms of arithmetic. Our next entry uncovers their secret rhythm hiding deep within chaos. But here's the big question. As numbers get larger, how often do primes appear? Is there a hidden rhythm inside this numerical chaos? Enter the prime number theorem, proved independently in 1896 by Jacques Hadamard and Charles de la Vallée-Poussin. It revealed a stunning pattern. As numbers grow, the density of primes decreases, and this decay follows a specific logarithmic pattern. This wasn't just a statistical trick. It linked primes to complex analysis, specifically to the mysterious Riemann zeta function, which still hides secrets we haven't unlocked. The prime number theorem didn't just tame the chaos of primes, it became the backbone of modern number theory. It showed that even in randomness, math finds structure. Before we get to the final two, here are 5 brilliant problems that almost made the list, but still deserve a standing ovation. Basel problem, solved by Euler in 1734. What's the sum of all the reciprocals of the squares? That is, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. Nobody knew, until Leonhard Euler shocked the world with the answer, pi squared over 6. He connected an infinite series to geometry pi, of all things. A landmark in mathematical elegance. Goldbach's conjecture, still unsolved, partially proven. Every even number greater than 2 can be expressed as the sum of 2 primes. Sounds simple, right? It's eluded proof for over 280 years. But massive progress has been made, some even proving it for numbers up to 4 times 10 to the 18th. Still, no complete proof. The Apollonius circle problem by the ancient Greeks. Given 3 objects, points, lines, or circles, can you find a circle tangent to all 3? The Greeks cracked this over 2,000 years ago, a masterpiece of classical geometry, and still taught today. Hilbert's 17th problem, solved by Emil Artin in 1927. Can every non-negative polynomial be written as a sum of squares of rational functions? Emil Artin said yes, and his proof reshaped real algebra. It's one of the lesser-known Hilbert problems, but crucial for understanding the nature of positivity in math. Riemann mapping theorem, proven in the early 20th century. It says any simply connected region, no matter how weird, can be mapped onto a perfect circle using a conformal transformation. Elegant, abstract, and essential for complex analysis. It's geometry, on a whole other level. 5 legendary problems, some ancient, some almost solved, but each a milestone in the history of mathematics. Now, it's time for the final 2. And now, we enter the top 2. This next one asked a question about spheres and dimensions, and was solved by a man who vanished into legend. Is a donut the same as a coffee mug? In topology, the answer is yes. Topology is the study of shapes that can stretch, twist, and bend, but not tear. In 1904, Henri Poincaré asked a bold question. Is every 3-dimensional space that behaves like a sphere actually a sphere? It became known as the Poincaré conjecture, and solving it meant understanding the very shape of the universe. For nearly a century, no one could crack it. Then came Grigory Perelman, a quiet, brilliant mathematician from Russia. In 2003, he posted a proof online. No journal, no fanfare. He used a tool called Ricci Flow to smooth out complex shapes. His work was stunning. The math world held its breath, and after years of checking, the verdict came. He had done it. Perelman had solved one of the 7 Millennium Prize problems. And then, in one of the most shocking moments in modern science, he turned it all down. The Fields Medal, the money, the fame. Perelman vanished from public life, saying, "I'm not interested in money or fame. I don't want to be on display like an animal in a zoo." He solved one of the deepest mysteries in mathematics. and reminded the world what pure devotion to knowledge really looks like. And finally, 358 years. One of the most iconic riddles in mathematics, born in a book margin and solved by a man who kept it secret for 7 years. In 1637, a French lawyer named Pierre de Fermat scribbled a simple note in the margin of a math book. It is impossible to separate a cube into 2 cubes, or a fourth power into 2 fourth powers, and so on. Then he added, "I have discovered a truly marvelous proof, but this margin is too narrow to contain it." That sentence became one of the most legendary puzzles in mathematics. Fermat's last theorem, for n greater than 2, there are no whole number solutions to a to the n plus b to the n equals c to the n. It looks like high school algebra, but it took 358 years to prove. Over the centuries, great minds tried and failed. Mathematicians proved it for specific exponents, 3, 5, 7, 100,000. But a general proof? Nothing. Then came Andrew Wiles, a British mathematician who first encountered the problem as a child. He dedicated 7 secret years of his life to solving it. In 1993, he presented his proof, 130 pages of deep mathematics involving elliptic curves and modular forms. The room was electric. Then a flaw, a gap in the logic. Months passed. Some feared the dream was over. But with the help of a former student, Wiles found a way. In 1994, he finally, completely, proved Fermat's last theorem. It wasn't just the longest-standing open question in mathematics. It was a human story of obsession, resilience, and brilliance. A centuries-old mystery, solved by one man, who never gave up. A boy's dream, a man's legacy, a final answer to Fermat's impossible riddle. These weren't just math problems. They were obsessions, mysteries that outlived their creators. Some took centuries. Others rewrote the rules of reality. What do they all have in common? They remind us that math isn't cold or mechanical, it's deeply human. It's the language of curiosity, persistence, and imagination. So now it's your turn. Which of these legendary problems blew your mind the most? Let us know in the comments below. If you enjoyed this journey, give it a like, subscribe, and ring that bell so you never miss another deep dive into the brilliance of the human mind. This is Real Life Top 10s. Thanks for watching, and we'll see you in the next one.